Hello everyone, I'm just going to present some solution notes to this year's 2022 AMC12 A, number 25. So the problem goes like this. A circle with integer radius is centered at RR. Distinct line segments of length CI connect 0i to BI0 for i between 1 and 14 inclusive and are tangent to the circle, where the AIs, BIs, and CRs are all positive integers, and the CIs are in non-decreasing order. So we want to find the ratio C14 over C1 for the least possible value of R. So we need the biggest hypotenuse over the smallest hypotenuse. So let's just understand what the problem is saying first, right? So you have some circle, has some radius, R, it's centered at R. And then it says you have some line segment that goes from the x-axis to the y-axis is in a tangent to the circle. So this line segment, it could be like this. Technically, I guess it could be like this. Or it could be like that. And it would be basically the excircles of this triangle, this triangle, and this triangle. The circle would be the excircle of those three triangles in those three configurations each. But the problem says that AI and BI are positive integers. So they can't intersect at a negative coordinate. So let's just erase that. Okay, the only other configuration is that the blue circle is an incircle of the right triangle, and that's also possible. So it's either the excircle or the incircle of some triangle in the first quadrant with the coordinate axes as the legs. Okay, so let's just review some facts about inradii and exradii that hopefully you know. So if you have a, let's say, incircle of a right triangle, then one formula for the radius of the incircle, say it's ABC, is A plus B minus C over 2. You could also just write it S minus C, where S is the semi-perimeter. So if you want to prove this, it's just using the fact that basically, if you draw the two radii to these two legs, this is a square because the rectangle has two sides are congruent that are adjacent. And then so finding the inradius of this triangle is equivalent to finding the length of the tangent from point C to the incircle. So by equal tangents, the two blue segments are equal. Let's label it Z. By equal tangents as well, these two are equal, so that equals that. From, let's say, A to this point, let's call it S, and maybe we'll call that R. So AR is RAS, and maybe we'll just call this X and X. And then these two tangents from B to the incircle are also equal. Maybe that can be like Y and Y. So then if you're given A, B, and C, let's say A, B, C given, so that the only variables are X, Y, and Z. If you want, imagine 3, 4, 5 are the triplet A, B, C. Then you just have to solve the system of equations. Z plus Y equals A, Z plus X equals B, and Y plus X equals C. Adding and dividing by 2, we get the semi-perimeter is equal to X plus Y plus Z. Subtracting, and we see that Z is equal to S minus X plus Y. But X plus Y is just, the hypotenuse C. So we can just say S minus C. And Z was the tangent length from the right angle vertex to the incircle of the right triangle. So this is also the radius, the length of the opposite side of that square. Okay, so we found that in any right triangle, this formula only works for right triangle, it doesn't work for non-right triangles. The radius is s minus c, or if you want a plus b minus c over 2, because this is just equivalent. Okay. Obviously, if you want the inradius normally, you would do area over semiperimeter. So that's the inradius of a right triangle. You can also have an excircle, right? So here, this circle, it's like tangent to all 3 sides of this green triangle. It's tangent to the extension of CA past A, it's tangent to the extension of CB past B, and it's tangent to AB. So because it's tangent to all 3 sides or their extensions and it's outside the circle, it's called an excircle. It's the C excircle. So, there is a formula for the radius of an excircle, which maybe I won't derive. The C excircle has x radius area over r minus c. Sorry, s minus c. So you just replace this s with an s minus c. That's just, and this would work in any triangle. This is any triangle, this is any triangle. So if you have an excircle here, this is r sub c, that's the x center, I sub c, and this is c, and this is capital C. And so you do the area over s minus c is this x radius. But we'll just use the other formula, which is, note that in any triangle, if you have A, B, and C, then the sum of the 2 tangents from C to the excircle, so let's say like this line and this line, 2 points T and S, that's equal to the perimeter of ABC. Because by equal tangents from B, those 2 are equal, let's call that point R. By equal tangents from A, these 2 tangents are equal. So you can see that the sum of the green segments is equal to the perimeter. CS plus CT equals CA plus AT plus BS plus CB. But then this is equal to the other tangent, this is equal to the other tangent, and this is just the perimeter. So this is AB plus CA, that's AB, that's CA, and that's CB. Okay, so hopefully if you're attempting this problem on the AMC, you already know these 2 facts in advance. So here, if this is A and this is B, and let's say AB is length C, then we know that the sum of these 2 lengths, let's just do it in purple, B to that point, A to that point of tangent C, is just, well, these 2 add up to C, right? Okay, so on the one hand, the 2 adjacent sides of this rectangle is R plus R, where R is the x radius in the problem. On the other hand, R plus R is this length plus that length, but those 2 lengths add up to the perimeter of ABC, like I just said. It's B plus R minus C plus R minus A plus A, which is 2R. And of course, these 2 add up to C. Okay, so here, because it's a right triangle, this x radius is just the semiperimeter of ABC. Okay, so now we have all of the background information. R sub C is, like A plus B plus C over 2. Or rather, we should just write it 2R is the perimeter, where when it's an excircle for this right-angled triangle. And then the inradius is just, well, 2 times the inradius is this minus 2c, which is 2s minus 2c, which is a plus b minus c. Okay. So let's see if we can. So the problem says something about, you have to find the minimum value of R such that well, first off, I guess we should, yeah. So first off, we should see, let's see, is R R should be a integer because A, B, and C are all integers, and R is half the perimeter. So yeah, it should be fine when it's an excircle. So we should check that for all Pythagorean triplets A, B, and C we find that this is an integer, which should be the case. The top should be even, and this is an integer, which should be the case because if you have like some Pythagorean triplet, unless all three numbers are even, then two of them are odd. The hypotenuse is odd, and one of the legs is odd. But we can check that later. So we'll just assume R is an integer for now. So basically we need to choose the smallest value of R such that there's 14 values for C. Like 14 kind of distinct values for the hypotenuse length of our right triangle. So let's just let's just plug in the Pythagorean relationship, right? So let's do the excircle case. Excircle. So here, this was R and R, and we had something like A plus B plus C, which is A squared plus B squared, is it's 2 times R. So here, I guess we should isolate that. And then we can just square both sides. Let's square it over here. That should be a 4. Okay, so we can kind of see, those two cancel. And we're just left with some equation. Let's just divide by 2. R squared minus 2AC minus 2BR minus AB is, I guess this should be a positive sign. Yeah, that's negative and that's negative. Equals 0. Okay, so one thought I had was, there's 2 ways we could potentially apply some Simon's favorite factoring trick to this expression. One is we could add AB to both sides, and then it would just be upon division by 2, something like, this is an R. So R minus A, R minus B is AB. But that's not so good since, it's actually AB over 2 when we divide by 2, I suppose. Because AB could sort of vary as R is constant, possibly. The other way is just to do Simon's favorite factoring trick on R, which seems more natural since R is kind of, the main variable here, and A and B are sort of like the integer lengths we have to find, so we can try values for A and B. So by Simon's favorite factoring trick, let's see, so maybe we'll just add 2R to both sides, 2R squared that is. So we get AB, if I write it backwards, minus plus equals 2R squared. And then this just factors A minus R, B minus R. So we're trying to factor, these 3, so we have to add an appropriate constant term so that it factors, and that was 2R squared to both sides. So now, so that's one equation if it's an excircle. Let's just first check, what's the incircle equation, although you might not do this in this order on the test because you want to finish your line of reasoning. So in the incircle case, right, here it was like A plus B minus C over 2 is R when the radius is an incircle, so it would look like that. And then, so A plus B minus this equals 2R. But notice here, right, so you get negative C is 2R minus A minus B. So this is the exact same equation as this. So let's just highlight them, right? So if you square both sides, right? Let's unhighlight this one actually. So the only difference is that there's a negative here and there's a positive there. So when you square both sides, you get the same equation. And there might be some extraneous solutions because our conditions are that R, A, and B are positive integers. Okay, so upon squaring the two highlighted equations, they give the same equation. So they'll both reduce to this Simon's favorite factoring trick reduced equation. Okay, so that means both our cases are kind of, gotten from, like, we can analyze the same equation for both the incircle and excircle case. So let's just try values for R, right? We want the smallest value of R. So what if R is 1, right? So maybe it's like an incircle of a 3, 4, 5 right triangle. So let's try R equals 1. So A minus R is 2R squared. So there's two solutions for AB here, right? AB is an ordered pair. And, basically this could be 1, 2, 2, 1, right? It's the number of factors of 2, so 2 solutions. The problem does say, distinct line segments, CI, right? So it could be that some of the CIs are the same line segment. Are equal in length, but different line segments. That could happen if, I guess if you fix the inradius or exradius, the only way that can happen is if the reflections over the line y equals x. So you could have both of these work. Maybe this is a 4 by 3. Maybe this is a 4 by 3 that way. So there both hypotenuses are 5, but these are distinct line segments for the hypotenuse. So they count as different values for the 14 values of C that the problem mentions. Okay, so we need to find a radius where there's 14 of these segments, right? So maybe there's like, a couple of segments there and a couple of segments like on the outside. So there has to be 14 of those segments, not all necessarily distinct in length. So, okay, so now let's try R equals 2. So this only gave 2 solutions, right? And A and B have to be positive, so we're not allowed to say -1 and -2 for A minus 1 and B minus 1, because then here A is 0, and here B minus 1 is -2, so B would be -1, but the two legs can't be length 0 nor -1. Okay, so when R is 2, R minus A, maybe it was like A minus 2, B minus R, this is 2R squared. Okay, so here, this is 8, so there's 4 factors of 8, and all 4 of these will lead to positive valid values for A and B as integers, so that's fine. So this gave the number of factors of 8, which is 4. And in general, we can kind of see, it's just the number of factors of this number, right? So A minus 3, B minus 3 will get 2 times, 3 squared is 18. So this has 6 factors, so there's 6 solutions. None of the solutions can be negative, because if we try like the closest negative solutions, this would give A is, 0, and B is negative. Okay. R is 4, we get the same thing. Let's just check these more quickly now. So 2 times 4 squared is 32. This has, so the first factor could be any power of 2 up to 32. There's 6 of these, so there's 6 factors of 32 and 6 solutions. And neither of these can, both factors can both not be negative. We should check R equals 5, so we'll have 2 times 5 squared. This is 50. There's 6 factors of 50, so there's 6 solutions to this. If we try the closest 2 solutions that are negative, this won't work. It will give negative values for A and B. And then let's try r equals 6. So a minus 6, b minus 6 is 2 times r squared is 72. So here, you know, I guess, let's see, so 72 is 8 times 9, 2 cubed times 3 squared. So there's 4 times 3 solutions, right? So 12 solutions when both factors are positive. For instance, it could be 1 and 72. Oh, my bad. I think I forgot the 2, right? Yeah, there was a 2 somewhere. Yeah, this should be a 2, my bad. None of the analysis we've done so far is incorrect, but there should be an a minus 2r. So this is just times 2, this is times 2, this is times 2, this is times 2. For each of the previous cases, there's no, you know, negative solutions because this number is always double that number. So we can't have one of a or b be 0. So this should be times 2 and times 2. So let's just, you know, b minus 12, b minus positive 12 is 2 cubed times 3 squared. So here, there are 12 positive pairs, like 1, 72, 2, 36, dot, dot, dot. There's 12 solutions like that, because there's 12 factors of 72. Then you have to check, can both factors be negative, but still give positive values for a and b, right? The closest two values, so 72, could be like -8 and -9. So if -8 is equal to the factor that's, you know, a minus 12, -9 is equal to the factor that's b minus 12, then here, sure, yeah, a, b could be, you know, like 4 and 3. Or 3 and 4, so 2 solutions there. So 12 plus 2, that's 14. That's exactly the number of solutions the problem statement said. We needed to find, you know, the least value of r, for which there are 14 distinct line segments that are tangent to that circle in the quadrant 1. So we found r is 6 works, and no smaller value of r works, so r is 6. Okay, so maybe at the start I should have said, you know, what is it actually asking, right? Because this is a confusing question. It's asking, we need to find the least, what's the least value of r for which there are 14 distinct line segments that are tangent to the circle with radius r centered at r, such that both of the x and y x-intercepts are integer coordinates. So we see that 6 works. And the 2 negative solutions for a minus 12 and b minus 12, they were just when it was like an excircle and not an incircle. So, you know, this one would be the, you know, so here you have like 4 and 3 and 5, and then 1, 2. So here, sorry, this should be 2, this should be 3. So here, this is an excircle, right? 4, 3 for AB means the circle is an excircle. If you take one of the other solutions like 1 and 72, this means A is 13, B is 84. So that's a 13, 84, 85 triangle. So that would have inradius 6. I mean, inradius 6, yeah. So A plus B minus C is over 2 is 6. So there's 6, you know, Pythagorean triplets with the r equals 6 as the inradius of the Pythagorean triplet. This is one of them. You know, another one could be like 3, 4, 5 scaled up by, this is inradius 1, so if you scale it by 6, it'll be 18, 24, 30, and the inradius will be 6. So that would be another one of the solutions. You know, this would be like a minus, this is 6, this is 12, right? So 6, 12 corresponds to a equals 12 more than that, b is 12 more than that, and yeah, so a minus 12 is 6, b minus 12 is 12. That gives a equals 18 and b equals 24. So that would be another valid Pythagorean triplet where the inradius is 6. So yeah, we see, you know, there's 7 values where the inradius or exradius is 6, and it's a right triangle. and the x radius is opposite the right angle. But then there's 14 distinct line segments because you can always, switch the value of A and B and get another valid triangle, which is distinct in the problem. So finally, it just asks what's the biggest hypotenuse over the smallest hypotenuse for the smallest value of R, which gives 14 solutions, which we found is 6. So here, the biggest one would be, well, if you think about it, it's pretty clear that the bigger the slope, the bigger the hypotenuse, right? If you fix the radius to be 6, then if it's close to slope -1, the hypotenuse is small. If it's close to like -6 for the slope, the hypotenuse will be bigger. So this solution corresponds to, like where they're furthest apart, where they're 71 apart. This gave A equals 13, B equals 84. So this is, the Pythagorean triplet with those as the leg, which is 85. So C14 is 85. And then C1 is the smallest hypotenuse, which is when the circle is an excircle and the triangle is tucked between the circle and the axes, and there it had hypotenuse 5 because it was 3, 4, 5. So the biggest hypotenuse over the smallest hypotenuse is just 85 over 5 for the smallest value of R that gives 14 distinct line segments. Okay, so yeah, this problem, it's doable if you know your inradius and exradius formulas for a right triangle. There are other ways you can derive them. For instance, if you just do K over R is S, or R is K over S, and then you plug in 1/2 AB, and then you plug in, A plus B minus C over plus C over 2. This is another inradius formula when it's a right triangle. And if you just use the Pythagorean theorem on this, you should also get the same formula. So somehow, you can simplify A plus B plus that equals that. It should just be the same. Like any two of these equations should give R minus or S minus C equals the inradius for a right triangle. So semi-perimeter inradius, this is a right triangle. Yeah, so Pythagorean theorem, the equal tangents, and so yeah, there's two ways to derive the formula R equals S minus C for the inradius of a right triangle. You can do it the way we did it, or you can use the regular inradius formula and Pythagorean theorem. Okay, so that's probably it for this video. I might make a few more AMC videos in the future. For those taking, the AMC12 B this year in 2022, good luck. If you're taking the 10B, also good luck. Have fun, don't be nervous. Try to relax and play the night before and the hour before the test a bit if you can, so you can be in a more relaxed and playful mindset going into the test. If you have any thoughts, comments, or questions, you can leave it in the comments below.